Okay, so this is our last class for Stat 644, and you made it. Believe it or not, you made it, and you're here. And we're going to go through all the material tonight just to get everybody feeling better about the final exam. And if you have any particular questions you want to go over, I can answer those. And we're just going to go through the entire book, and I have little tips and tricks that I like to add to all of the material, and so I hope that you find it beneficial when you're reviewing for the final exam. And since this is a small group, just 3 of us plus me, 4 of us tonight, we can make this conversational. If you want to interrupt me at any time, please do. But I would just ask that you speak up instead of using the chat box, just because it's easier for me to interact with you that way. So if you want to just interrupt me and ask a question, by all means go ahead, and we'll go through the material, the whole book, and if questions come up, we'll answer those. And if we get done early, then we get done early. But that's my goal for tonight, is just to make sure that everybody has kind of a synopsis overview of what this class has been all about. And I hope that you find it interesting, because I personally love statistics, and this class particularly is a really good class, and I like the textbook a lot. So I'm hoping that you've had a good experience here and are feeling prepared to take the final, and I hope that you feel that you learned something. So does anybody have any questions to start us out tonight? Okay, well, just speak up if you think of something, and we will get started here. It's a crazy week for me. I'm sure it's a crazy week for you all too. This time of year is just crazy in our line of work, and so we're here anyway, right? Okay, so I'm going to share. What am I going to share here? I'm going to share this. Okay, so I'm sharing my document camera screen. And so I'm not going to be looking at the chat box. So if you need to get my attention for anything, please just speak up into your microphone and I'll hear you. So let me get my little notes ready here. Okay, so we started out chapter 1 by talking about descriptive versus inferential statistics. Let me get my angle right on this. Okay. We talked about descriptive versus inferential statistics. And of course, the difference is that descriptive statistics simply describe a data set. I mean, I could sit here and open up Excel and type a bunch of numbers in and tell it to give me an average or a standard deviation or a median or quartiles or whatever. And all it's doing is just a lot of basic arithmetic over and over and over again to get me those types of pieces of information. Averages, what we call a mean, standard deviation, all that is simply just a product of doing a lot of rote basic arithmetic. And so simply put, all that is doing is describing the data. Now, inferential statistics, which takes up the greater majority of all statistical study, is inferential statistics. And that is very different. That is where we jump from simply making a calculation to making educated statistical guesses. And so whereas descriptive statistics is simply for describing a set of data through arithmetic, this is actually making guesses about the data and what the data is telling you. And so anytime that you're making a guess, of course, you have a probability that goes along with that, a probability that your guess was right and a probability that your guess was wrong. And so that is what really distinguishes descriptive from inferential statistics, is that descriptive statistics are facts. They're facts. And then these are guesses that have a probability of being right or wrong. Okay. So I hope that that clarifies those definitions a little bit. Most of the statistics that are actually useful in the world, things that you actually do, are inferential statistics. If any of you are in Roanoke, there's a major accident on 81, and it's gotten everything all completely collapsed. So, okay. So we have experimental or observational units, and I think Susan just came in. Hi, Susan. If you need me, just speak up, because I won't be looking at the chat box. But this is going to be a very informal type of meeting, and if you need to speak up to ask any questions, please do. We're just going to run through the textbook from chapter 1 to chapter 13, or whatever the last chapter is. 13 sounds high. Chapter maybe 8 or 9. We're just going to run through it. So if you need me, just say hello. So an experimental unit is an object about which we collect data. This is going to be essentially a people. And most of the stuff in this class we've been doing, we've been talking about people as experimental units. And then, of course, the population is all of those units all together. The interesting thing about populations is that they are kind of theoretical. You may say that you're interested in, finding out what a certain age demographic thinks about something. So the population that you're interested in are all of the people that fit into that age demographic. But it's impossible to talk to every single person that fits into that demographic, because you can't find them all. You can't talk to them all. Even if you send out surveys, not all of them are going to respond. So the population is kind of like this theoretical idea where we know the idea exists. We know that there is a countable set. If you're thinking of like different types of infinities, it's kind of how I think of it in my head. You have different people that you can count, and the population is countable, but you're not going to be able to reach all of those people. And so while the population is kind of a real idea, it's not practically accessible to the statistician. In educational research, if we're interested in how a teaching technique has impacted students, we may survey a sample of people in a particular class or a particular school, but really if we're trying to generalize to how that teaching technique would impact all 9th grade English students, we're not going to be able to talk to all 9th grade English students, not even in the whole state, not even in the whole city of Roanoke, or city of whatever city you're in. So you have to be realistic about that and recognize that a sample is what we can access. We can access the sample, but we cannot normally access the population. That's the importance of those two ideas. Of course, the variable is the characteristic that we are studying. So then we started talking about how to display our data in a descriptive way. And so we looked at bar graphs and pie graphs and Pareto diagrams. And I wanted to mention the difference between a bar graph and a histogram. Bar graphs are for categorical data, and histograms are for numerical data, and the x-axis is the natural number scale over which the variable occurs. And that's why the bars touch each other, is because it's representing a continuous number scale, whereas a bar graph is representing categorical, which are discrete variables. And if I happen to show how messy my desk is right now on camera, please just ignore that and pretend like you never saw that, because it's really beyond my personal standards at this point of the year. But that's what the summer's for, right? So we talked about skewness and how that plays into the mean and the median. Let me just move this up a little bit. Okay, how that plays into the mean and median. So we have, this is right skewed, which looks kind of weird. I try to remember that this is kind of backwards from how it would logically seem. This is right skewed, which means the tail is longer on the right. So, you know, you would kind of think that if your distribution, you know, was like this, then that would be right skewed, because it's all going over here. All the data is going over there, right? Well, the skew talks about where the tail is. So this would be left skew, because the tail is so far skewed out to the left right here. That's what the skew is talking about. So this is a right skew because the tail is longer and bigger going out to the right. And that's going to reflect how the mean and the median relate to each other. So if you have a symmetric distribution, the median and the mean are together. If you're skewed, the mean is closer to the skewed end always. So if you're right skewed, then the mean is going to be to the right of the median. If you're left skewed, if you are left skewed, which would look like this. You can ignore all this stuff. This is just scratch paper that I reuse. If you're left skewed, then your mean is going to be to the left of your median. And so the mean always follows the same direction of the skew. So if you're really skewed, and this is, this is really, you know, like kind of dramatically skewed. My mean is actually probably going to be farther towards the tail than that even. It's probably going to be like over here somewhere. But either way, your mean is always going to follow the same direction of the skew. So if it's left skew, then your mean is shifted left. Okay? If it's left skew, then your mean is shifted left. I hope that makes sense. And if you have any questions, please just interrupt me and ask. Otherwise, I tend to just kind of get on a roll and start talking for hours, as I'm sure you know. You know that feeling being a teacher. Okay, so there's a picture of left skew and how the mean is skewed to the left. So same thing. Okay, so here's the variance. Here's variance of a sample. And of course, nobody really ever does this by hand, but this is how you do it. You take the individual data points, you subtract the mean, the sample mean from it. You take that difference and you square it, and you add up all of those, all the little individual units from 1 to n, and you divide it by the degrees of freedom, which is n minus 1. Degrees of freedom is just a fancy way of saying the number of freely varying data points. So we just take the number of data points and subtract 1, and that's how many of them are freely varying based on each other. And then that gives you the variance, which is s squared. But the standard deviation is simply the square root of this. So if you square root this entire thing, you square root this entire left side and this entire right side, then you'll get the standard deviation, which is just this whole thing under a square root. So this is the basic kind of arithmetic I was talking about. Nobody actually does this by hand unless you really don't have anything better to do with your time. We all, everybody just puts it into a calculator, or I just use Excel is honestly the easiest thing to do. But you can do it by hand. It's simple enough. There's nothing complicated about it. It's just basic subtraction and squaring and adding and dividing. It's just those 4 operations, and that'll get you there. If you're going to do it by hand or by kind of manually, and you want to use Excel, it's really nice to set it up into a table like this, where you just have each individual data point where you've subtracted the mean from it, where you've squared it, and then you just add all of those things up. You sum up all of these guys here, and then you take that, and that's now your numerator, and you divide by n minus 1. And that's another way to do it, just kind of not automatically. You're kind of doing it manually, but it just helps you organize your steps. Okay. So let's take a minute here, and I want to just clarify a couple of things that I know can confuse students sometimes. So I talked about this idea of a population versus a sample. Okay, so the population is kind of this like idea, that the population is up here. Okay, let me give you an example. If we're interested in all statistics students in the United States, okay, or all graduate school statistics students in the United States, you know, there is a countable number of those people. If we really had the resources and the time, we could actually collect all of those people's names and actually count that. It's a countable number. It's a countable set. However, getting in touch with all those people and asking them how they feel about doing a chi-square test is a different story altogether. And so from the population, which exists and is countable and is real, and since we can count it, we could theoretically talk to everybody, and get their responses, and then do the descriptive statistics of those. So the mean of this population and the standard deviation of the population, they exist. We just don't have any way to get those numbers, but they do exist, right? Do you see how in theory they exist? And in fact, it's not even in theory. They do really exist. We just don't have access to that information. That's mu and sigma. That's your mean and your standard deviation that we've come to learn and talk about that way. What we can do, what we can actually do as human beings, we can pull a sample. We can pull a sample, which is actual number of people that we can talk to. And these 5 gorgeous stick figures are going to represent the idea of a sample. So I've taken this sample of people, and these people are the ones I can actually talk to. And these people, I can ask a question, and they can give me their answers, and then I can take those and I can find a mean or a standard deviation or a whatever. And that I can actually gain access to through experimental design. And that is X bar and S. That is my sample mean and my sample standard deviation. That is why we have 2 different things. Now, we can say that, of course, if the sample is well chosen enough, then it's going to be representative of the population. And so X bar would approach mu, and S would approach sigma. And we are guaranteed that mathematically by the central limit theorem. It says if we go to the population and we pull a sample and we get an X bar and an S, and then we go back to the sample and we pull, or excuse me, the population, and pull another sample that gives me an X bar and an S, and another sample that gives me an X bar and an S, and another sample that gives me an X bar and an S. And I can do this as many times as I want because I know who's in the population. I can go back and pull another sample. And then the averages of all of those X bars and S's are normally distributed, and the averages become the true mu and the true sigma. So that's how we're guaranteed that mathematically, is that we're basically going and finding a sample, and we get an average, and then we do that a million times, or not a million times, but we do it a lot of times, 100 times, 200 times, whatever we can do. And then the average of those averages is really approaching that number. So that's what the central limit theorem tells us. And that's why the idea of a sample is so important, because it's the sample and the distribution of the sample means and the sample standard deviations. We call it a sampling distribution. And it's the sampling distribution, the distribution of the sample results, is what we actually have direct access to and what we can use to analyze and make inferences and make, guesses and things like that. It's all coming from the sample distribution, which is a collection of all possible samples, basically. And those allow us to get indirect access to this population. And the population is what we're actually seeking to answer a question about. So it's kind of like the statistician's paradox. I want the population, but I can't actually get that. It's real, but I can't grab it. It's just out of my reach. So in order to get a pretty good, a 99.9%, accurate estimation of that, I have to do samples over and over again. And of course, then we know, even back in elementary school, when we were doing science experiments, we'd have to run the experiment multiple times, because if you run it once, you have nothing to base your answers off of. So if we run the sample many, many times, then each time we run it, it strengthens the other times that we've run it. So that's why we don't want to run a sample one time. And then if we take that idea and we expand it out kind of, to infinity, that's where the idea of a population comes into play. So I'm sorry if I'm harping too much on that, but it's a really, really critical idea in statistics, and I think it's really critical to understanding the material at a deeper level. And so that's all I'm going to say about that.
Alex,
Hi, yes.
Hi, this is Jennifer.
Hi.
When you theoretically do all these, hundreds and hundreds of samples, do you have to be careful that the people in the samples don't overlap, or does that matter?
It doesn't matter.
Okay.
Because each sample is randomly chosen. If the experiment is designed properly, each sample is valid because each sample has been randomly chosen. So even if you end up talking to the same people multiple times, it doesn't matter, because they just happen to be chosen, right? They just happen to be chosen a second or third time, but really they are being chosen through the same randomized process each time. Okay. So think of it like, if I go to a random number generator, random.org is one I use a lot, and I say, okay, I want randomly generated numbers between 0 and 100. Imagine that my population has 100 people. I'm boiling it down just to for the sake of the argument here. So imagine my population is actually quite small, and it has 100 people in it. When I'm going to random.org and I say, give me random numbers between 0 and 100, and it generates these things one at a time, I can generate a number, and then a couple clicks in, I'll generate the same number again, because it's only pulling out of 100 people. So each person has 1/100th of a chance of being chosen. And each time I'm pulling from, each person has an equal chance of being chosen each time. So if I happen to pull somebody a second time, it's okay, because I pulled them randomly and they just happen to get chosen a second time. So that's not going to throw off any results. It's not going to compromise the viability of your experimental design. As long as it's all been done randomly, it's perfectly okay to talk to the same people more than once.
Okay, that makes sense. Thanks.
Okay, sure. Okay, so we are going to move on to outliers. Outliers are essentially pieces of data that can be statistically ruled out from the rest of your data set. And you have to be very careful about this, because you may look at a data set and just visually look at the numbers and say, oh, this one's an outlier because it doesn't fit with the rest of them, right? It's kind of like, which of these is not like the other? But the danger in that is that there's no mathematical basis for that decision. And in statistics, the decisions have to be mathematically based. And then it's only at the very end that there's a bit of an art that comes into it. And the art is in the interpretation of the results. But through the process, the entire process is very mathematically based. So, and when I say art, I don't mean that there's no rules to it. I just means that you have to, it's kind of like an acquired skill trying to interpret statistical results. And you get better the more and more you do it. So outliers have to be within, or excuse me, without, not within, without 1.5 interquartile ranges down or up. And that's suspect. I would actually compel you to not always rely on that. And I would say that you would really only consider something an outlier if it's above 3 interquartile ranges out. And the interquartile range is, again, the difference between the third quartile and the first quartile. And so if it's outside of 1.5 interquartile ranges, it might be an outlier. If it's outside of 3, it's pretty much definitely an outlier. For a z-score, and again, I would encourage you to be kind of conservative with this. For a z-score, if your z-score for a data point is greater than 2, absolute value, of course, because signs on z-scores don't really matter because the distribution is symmetric. So a -2 has the same, statistical implications as a +2. So if it's outside of 2, it's possible. If it's outside of 3, the z value of 3, then it's definitely an outlier. And that is because when you get outside of 3, a z-score of 3, your tail area there is just so small that the chance of being out there is very, very, very small. And so the way that they make this determination about outlier and z-value is just based on the way the distribution is shaped and how the tails are shaped. Just coincidentally, now that we're getting into z-values, how comfortable are we feeling about a z-table and things of that nature? Reading a z-table and just understanding what a z-value is. How do we feel about that? Anybody need help with that? Okay. If you change your mind, let me know. I mean, I could talk about this stuff all day and night. So, okay. Probability. Probability is our next topic here. We're already in chapter 3, about a third of the way through the semester at this point. I'm getting tied up in my cords. I've got cords everywhere here. So probability, I want to go over a couple of things, and then as Dr. Mistely put up the flow chart, the probability flow chart, it looks like this. Looks like that. Has anybody seen this before? Is that on Inquire or D2L?
I haven't seen it, but that doesn't really mean anything.
Okay, so on page 158, and I will actually email this out to everybody tonight. I already have a digital scanned version of this. Let's see here. Prob flow chart. Okay, now that'll be my reminder. Okay, so on page 158 of the book is this. It's a nice little flow chart that just helps you organize all the different rules and ways to calculate stuff. And so you can kind of go through your scenario and it kind of just guides you right there to the right thing. The biggest thing to remember with probability and determining what you even use for it is just looking at the language. The language in the problem will give you the most hints. And so if you're looking at the word or, the probability of something or something, it's immediately a union. And so you're only looking at if they're mutually exclusive or not. And this is how you do this. And the only difference here is that if they're not mutually exclusive, meaning that one depends on the other one, then all you're doing is subtracting out the intersection. That's the only difference there. If you're looking at a problem and it's asking you for the probability of something and something else, then you're automatically looking at an intersection, only an intersection. And so you're looking at the multiplication rule, and you just have to ask yourself, well, is it dependent or independent? And then that changes the way that you do this, okay? If you're looking at the probability of not something, then that is the complementary rule. So you just are looking at the probability of the complement of that thing subtracted from 1, because anything and its complement has to have a summed probability of 100%. And sometimes it's an exercise in mathematical logic to even identify what the true complement of something is, but you have to be very conservative with defining complements, because there's a temptation to misrepresent something's complement, and truly it is just the opposite of that thing happening. If somebody just said, okay, what is the probability of I don't know, what's the probability of a tree branch falling outside next to my house? Well, I could say that it is 1 minus the probability of the tree branch not falling. So that, the temptation might be to say, well, it's, is it falling during a rainstorm, or maybe it's not falling, if it falls in the other yard. All I'm saying is the complement of any event is simply putting the word not in it. So the complement of the tree branch falling is that the tree branch is not falling. The tree branch doesn't fall, does not fall. And it's really no more complicated than that. And so if you think about it, the probability of the tree branch falling plus the probability of the tree branch not falling together, added together, those have to equal 100%, because one of the two of those has to happen, right? Something's either going to happen or it's not going to happen. And you're 100% guaranteed that one of those is going to happen. Sometimes I think I'm going crazy when I'm talking about probability, but it is somewhat of a mental trick, and just, not overcomplicating it. Probability can be very straightforward, as long as you don't, kind of overcomplicate it in your head. And then the last one is the conditional probability, where we have one thing given that something else is already the case. And so we write it like this: A given B and B given A. If they're independent, then one doesn't impact the other one. So if the probability of A given B is the same as the probability of A, that just means that if B is given, it's not changing A. So if the probability of B is whatever, it's not going to impact the probability of A happening. So whether or not B happens doesn't matter. The probability of A is still the probability of A. If they are dependent, you take the intersection and you divide by the probability of the given. And the same thing if if A is given. If A is given, you divide by the probability of the given, and you're still taking the probability of the intersection in the numerator. Questions? Okay, let's move on to...
Okay, I have a question.
Oh, yes.
Okay, I get messed up when they say the probability of at least one heads or at least one tails. Like, can
Okay.
you just give me a summary of that real quick?
So it probably, so for like coin flips, is that what you're talking about? At least one head
Yeah,
or
anytime they say at least the probability of at least one,
right.
whatever you're doing.
So that just means that that is your minimum cutoff. So if I'm looking at the probability of, let's do a little quick example here. Let's say I flip 4 coins. So I'm flipping 4 coins. It's my beautiful coin drawing. So I flip 4 coins. And I want to know the probability of getting at least, let's make it at least, probability of getting at least 2 heads, okay? At least 2 heads. So let's think about, so probability in general is the specific outcome we want divided by the total number of outcomes, which just makes it a percentage, essentially, a proportion of the total outcomes that are what we're interested in. So if we flip 4 coins, well, let's make it 3 coins just to make the example easier. 3 coins, and we want at least 2 heads. So I need to figure out all the ways for this to unfold. If I flip 3 coins, I'm either going to have heads, 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 tails, tails, heads, heads, tails, heads, tails, heads, tail, heads, heads, tails, 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 and tails, tails, heads. Okay. I know that there are 8 outcomes because it's a counting rule thing. So we have 3 coins. Each coin has 2 possible outcomes. So it's 2 to the 3rd power, which is 8. So I know I'm going to have 8 possibilities, and there's my 8. Now, my probability is going to be divided by 8 because that's my total number of outcomes. Out of those, what proportion are satisfying our condition here of at least 2 heads? So we have that one works, that one, that one, that one, right? At least 2 heads. Okay, so it's 4. So 4 eighths, which would be the probability equals 1/2. So really, when you're thinking about at least, all you need to do is just remember that probability is specific divided by whole or desired divided by total. And you just have to think about what scenarios and the outcomes would fit that criteria. Does that make sense?
Yes, thank you very
Okay,
much.
sure. Okay. So now we are in to random variables, random variables. And a discrete variable has to have a particular, has to take on a particular value. A continuous variable could take on any number of values in a range. So if it's discrete, the mu, the mean, is the sum of all of these x's times their probability of x. So the way that I like to think about this is that if you had, it's kind of like a weighted average. If you're calculating a student's grade and it's a weighted average, you're going to take each item, each assessed graded item, you're going to multiply it by the weight, and then you're going to, for the weight for that category, quizzes, tests, papers, whatever, and then you're going to add all of that together, and that's the student's grade. This is really the same thing. It's saying that the overall mean, or population mean, is the sum of all the individual x's times the p of x's. And the p of x's is just the probability of each of those x's. And so it's the same structure as a weighted average. That's kind of how I think about it. And those have to be discrete. Those are discrete variables are like that because they have to take on a particular value. Okay. The variance of a random variable, I recommend, this is on page 175. I really recommend using this formula for this. It's just what I think is the best way to do that. So here you're just taking each of the x's, each of the individual x's, you're squaring it, multiplying it by its corresponding p, then you sum all of that up, and then you subtract mu squared, and that'll give you your variance, okay, for the population. Come on. What's the difference between Chebyshev's and the empirical rule? Does anybody want to elaborate on that a little bit? What's the difference between Chebyshev's and the empirical rule? So the empirical rule is what we would, you know, in the common tongue, we would call the bell curve or the normal curve, normal distribution, bell curve, but no, whatever. It only works on things that are mound-shaped and symmetric. Chebyshev's will work on anything. It's much less precise, but it'll work on anything. So that's the difference. With the empirical rule, we get the classic 68, 95, 99.7 chunks of the distribution. With Chebyshev's rule, it's just a little bit more, it's a little bit less precise. It's 3/4 and 8/9 within the same ranges. This is in between 1 standard deviation, 2 standard deviations, and 3 standard deviations out. Okay, that's what this is saying here. Plus or minus 3 sigma, plus or minus 2 sigma, plus or minus 1 sigma. Okay. Okay. Okay, binomial random variables. Who feels comfortable about binomial random variables? Who feels comfortable with that? Really, all they are is just a kind of a special type of a scenario. I wish my document camera wouldn't fall. There we go. It's the binomial situation is really just a special scenario where you're only taking a certain number of observations. And as soon as you limit the number of observations, and you know how many of those are, how many observations you're going to take, the binomial setting for finding probabilities is simply just running through these big factorial equations. And the benefit of that is that it gives you a distribution that allows you to check for 2 outcomes each trial: success and failure. And a success is not necessarily like a moral or a valuable success. It's just a success as in the thing that you're testing for has happened. That's what the success is. I just wrote an exam question for the binomial distribution on an exam in a class I teach called Statistics and Social Justice. And so all of the questions and all the projects and everything are all social justice oriented. And so the binomial question was about the probability of people becoming welfare recipients for the first time. And so it's ironic to go through that and talk about, well, what's the success rate? Clearly, it's not a success if somebody is joining the welfare program, but it's mathematical, it's statistically, we call it a success because we're testing for that rate. And so when somebody does, when that happens to them, they are a statistical success in the equation because we're testing for this thing and it has happened to them. So we call it a success, even though it could be misleading to somebody that is not in statistics, and they might think that we're, you know, are heartless or have questionable values, but really it's just the nomenclature that we use. So we're looking at success and failure, and we're making sure that everything is independent. Each trial is independent, and each of them has to be identical. And here's the thing. Here's the thing that's really key here. It has to consist of a set number of trials, and that's the whole thing. We're not just going to keep repeating samples and trials over and over and over again until we're satisfied. We have to set at the outset, we have to say, okay, we're doing this 10 trials, and then that's all we're doing. We're not changing that. You have to know from the beginning, otherwise the calculation is different and the experiment is different. So that is that. Okay. I love some of these notes that I leave for myself. On page 187, I wrote, study this. So this is probably a good thing for you to study. This is the binomial probability distribution. This is the formula, essentially, for doing this. This is a fairly abstract way to write this. If you're not too brushed up on your probability and, or excuse me, on your combinatorics nomenclature, this right here, this n over x in the parentheses might seem strange, but what this is this is saying that the probability of our binomial random variable, okay, our binomial random variable having k successes. So whatever the binomial random variable is that we're looking at, having k successes, is oh my gosh, I just lost my train of thought. It's the factorial of n over k factorial 1 n minus k factorial that is what that n over x means right there. Okay, and I think I've done that right. 4, 3, yep. N over k, and then n minus k factorial, and then we multiply by the probability of each trial having a success to the kth power times 1 minus p to the n minus k. And that's exactly what this is saying here, just in different nomenclature. So I like to just remember that Q is simply the complement of P. Q would be right here, is simply the complement of P. So all you're doing is you're taking the probability, raising it to the K power, then you're taking the complement of it and raising it to the N minus K power. And then this is simply just a combination here, okay? So I hope that might clarify what all of this means, but maybe not. I hope that it does. So for example, if I said, okay, the probability of a new person becoming a welfare recipient was 0.4, I'm going to look at this over n equals 10 years. Let's look at it for a decade. And then I'm interested in 3 successes, or three out of the n. This is 3 out of the n. So this would be 3 years out of 10 years, somebody becoming a new welfare recipient. So then I would just go through and I'd plug all of those things in right there. So the probability of our binomial random variable, which is the number of years of successes out of our total 10 years, x equals 3, okay, is our n squared over k squared n minus k squared times p to the k times 1 minus p to the n minus k. So that's all we're doing. This is 10 years. This is 3 years where somebody's become a new welfare recipient. It's kind of a dark example, but it's just on my mind because I just put it on an exam yesterday. So here we just have the 10 factorial. Here we have 3 factorial and 7 factorial. I mean, you can do all of this in your calculator. I believe that's 0.064. And then this is 0.6 to the 7th power, which I don't know what it is off the top of my head. But I like to just take a minute and look at this. This will simplify because the numerator is simply this. And all that stays the same. But if you notice that these 7 factorials cancel, so really you're just left with this 10 times 9 times 8 over 6. 3 factorial is equal to 6. And so then you just have the decimals out here, blah, 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 and you'll do all the rest of it there, and that's that binomial probability calculator. That is the probability, the capital P of something happening, okay? When you're dealing with binomial random variables, and I want you to study this also, remember that your mean, your mu is n times p. Your variance is n times p times q, and remember that q is simply 1 minus p. So an equally effective way to write this would be that sigma squared equals np 1 minus p, okay? And the standard deviation is simply the square root of that. Okay, so for the binomial random variable tables here, I just, on page 189, I just want you to go down to the bottom of the page and read this little section right here. That will help you if you're having trouble reading a binomial random variable table. That will help you with that on page 189. So now we're into the z tables. For the normal distribution, for the normal curve, we're into the z tables. Oops. And if you have trouble reading a z table, I totally understand, and I'm happy to go through how to do that. I'm also happy to go through how to read it backwards. Because if you have a certain percentage of the area, percentage of the data points given to you, you also are able to work backwards and find out what z value corresponds to that. And that's how we know, just because we use it all the time, that's how we know that if we're dealing with a 95% confidence level, we want a z value of 1.96. I know that just because that's how you work backwards in the table to get that, and it's a common value. Would anybody like me to go over how to read a z table forwards or backwards? I'm happy to do that. Okay. If that comes up later, then please just speak up and let me know. So now this is cool. If your sample size is large enough, and I believe it is over 100, is it 100 or maybe it's over like maybe it's over, they say that the interval, okay, this is right. When n is large enough, you can actually treat the binomial distribution as if it's a normal distribution, which is really cool because then it solves all of those nasty equations into our regular old z-table and just use the z-table. So they say that if the interval mu plus or minus 3 sigma should lie within the range of the binomial random variable from 0 to n, if that's the case, if mu plus or minus 3 sigma, so that would be 99.7% of the data is within the range of the binomial random variable, then it's okay to use the normal approximation. And if that's true, then where is it here? Oh, right here, sorry. Then your z-value, excuse me, is simply your value of interest plus a half, 0.5, minus mu, and then you divide by sigma. So it's the same kind of a thing, whereas a regular z-value would just be the data point minus mu. This is just say, take the data point, add a half, add 0.5, and then subtract mu and divide by sigma. So that's pretty cool because you can bypass all the other stuff if you have a large enough data size. You don't have to do any of the binomial stuff anymore. Oh, excuse me. It's been a long day. So, central limit theorem I talked about, but let's go over it again. The central limit theorem tells you that when you are taking when you're taking samples and you have a sampling distribution from all of your samples, then the distribution of those samples, called a sampling distribution, that will behave like the actual population would behave when n is large enough. The language this book uses is sufficiently large. So when n is sufficiently large, it will behave like the real thing, like the real population. Okay. Or in other words, when you have enough samples, the average of the samples is the true mu or true sigma. Let's jump into a confidence interval. Boy, oh boy, a confidence interval. The confidence interval for z, okay, the confidence interval for z is x bar plus or minus 1.96. That's the z-value for the 95%. So whatever your z-value is for your confidence level, you would put that in there, times sigma divided by square root of n. This is the true sigma. If you happen to know the sigma of the x bar, then you can just put that right there. The reason you would divide by the square root of n is that it adjusts the standard deviation down for the sample size, which is important to do. It's called an adjusted standard deviation, or a standard error. I know Dr. Mr. League harps on this, but I'm going to harp on it too. The confidence interval does not mean how confident you are in how good of a mathematician you are. The confidence interval actually means that we are confident in the process that gave us that interval. We are confident that, so if it's a 95% confidence interval, and this is why the idea of a sampling distribution is so important. If we, oh, come on, things annoying me. If we are doing a 95% confidence interval, it means that if we run the test and we find the interval 100 times, 95 of them are going to actually contain the true mu, and 5 of them will not. And that's why we say we're 95% confident, is that the interval that we get will contain the true population parameter 95% of the time. That is what it means. And so we're introduced to this idea of alpha. Alpha is simply the tail area. The tail area beyond what you are interested in. So remember, and this all goes back to the empirical rule, the good old, 68, 95, 99.7 rule. So here's my lovely normal curve. Within one standard deviation plus or minus, we get 68% of the data. So right there, this is my alpha. This is my alpha. It's just the part that I don't have. It's the part that I don't have, the part that I don't have inside that interval. If I did this again, and I did 3 standard deviations, and inside of this I had 99.7% of my data, this is my alpha, and this is my alpha. It's the part that I don't want. It's always the part that you don't want, the part that's not included in your interval. So this would be plus or minus 1, excuse me, this would be plus or minus 1 sigma, this would be plus or minus 3 sigma, and this means a 68% confidence level. This means a 99.7% confidence level. It just happens to be that most of the time, we're interested in a 95% confidence level or something thereabouts. And so if we're doing that, then we say, okay, 95% of the data is in here, and this is alpha, and this is alpha. And if 95% of the data is in here, and the whole thing is symmetric, then these tails get 2.5 each, because there's 5 left over, right? And they each get 2.5. And so all we're saying when we talk about alpha is we're talking about the part outside of where we have drawn our divide. So if we divide this here and say we want 95, then the part that is left out is 5%. And so we would say alpha equals 0.05, or alpha over 2 equals 0.025. And so it can easily and quickly, and rightfully so, become very confusing, and you're thinking, I have no idea what any of this is talking about. But really, it's a very simple idea. It's you're drawing a line in the sand, and you're saying, I want this stuff, and then everything else is the leftovers, and that's the alpha. And so the reason that we're interested in alpha is that when we start to run a hypothesis test, it will give us a number, it will give us a tail value, and we compare it to the alpha value to figure out which one is larger. And which one is larger tells us which part of our hypothesis is likely to be true. So there's that. Okay. Okay. So this is a thing that this textbook does. This is not the end-all be-all decision for all statistics ever. If n is greater than 30, you can use z. if n is greater than 30, it's large enough, it's behaving enough like a normal distribution. The central limit theorem is at play enough, is impacting the data enough that it will behave like a normal distribution, and you can use the normal distribution, you can use z-tables, and you can use everything else that it comes along with. If n is less than 30, you have to adjust your plan. You have to go with the t distribution, which is not as precise, but that cutoff at 30 is kind of that's not a real like definite rule. That's something that this textbook does, but not every textbook does it. Some textbook, I'm teaching out of another textbook right now that has it at 40. And then there are some statisticians that think you should never use z because it's not, because you're always approximating your population. You're never really getting the population. And so to be more statistically responsible and more realistic and more true to the fact that no matter what you're doing, you're really only getting access to samples. There are some statisticians that think that you should never use z or the normal curve for anything because it is making too many assumptions. It's too bold. It's too idealist, essentially. And they're saying, no, it's too idealist. It's not truly giving you a good answer because you're being too liberal with the work. And so a lot of that is up to interpretation. I tend to be one that's kind of in the middle. I think if you're over 100, if your n is over 100, you can reliably use z, unless you're dealing with something that's really sensitive or really touchy. But if you're over 100, then you can use z reliably in the real world. For this book, it's 30. 30 is the cutoff. For whatever reason, they think 30 is good. So for everything you do in this class, 30 is your cutoff. If n is less than 30, you use t. If n is greater than 30, you use z. The other thing that you use t for is if you don't know sigma. If you don't know sigma, and n is not large enough, then you really should use t because you have to approximate sigma with s. And if it even says it right here, for large n, s will be a good estimator of sigma. That's very true. But if n is not large enough, then you'll be stuck using s as s, and it's not really a sigma. But to be on the safe side, if you don't know sigma and you do know s, you can actually use the t distribution and it'll give you a perfectly reasonable answer. That's what I normally do anyway. I use t more than z just because it's more kind of, it's more of the responsible thing to do. But notice that they both have astonishingly similar structure because they accomplish the exact same thing. They are a sample mean minus the mu over the adjusted standard deviation called the standard error. And so they both have the exact same format. This is how you would actually calculate the t statistic for the test statistic for that x bar. Same thing can be done for individual data points. Okay. And you have a t table in the back, runs the same kind of way as a z table. If you have small sample, a confidence interval for mu, using the t statistic is your point estimate here is x bar, and then you're plus or minusing a t of alpha over 2. That this is just saying you take your tail, your alpha, and you split it into both tails, and you look at the t value for that. not the t-value for the whole thing, because then you'll be off. And then you multiply by this standard error. And then if you know sigma, you just replace it and you use it, and you use z to go along with it. Okay. It's a good idea if you don't know sigma, it's a good idea to stay away from z. We're getting there. We're already in chapter 5 here. Looking like we're on time. And a lot of the stuff that's coming after this is really just formulas and learning how to read questions and plug in the right formula where you need it. Now we're going to look at proportions of populations, or in other words, percentages. So if you're asked a question like, what percentage of the population does this? That's where you're going to want to use this. Proportion and percentage mean the same thing. And so the proportion of the sample that satisfies whatever criteria you're interested in is your p-hat. And your p-hat is simply the number of successes, divided by the total number of people in the population. Right here, it's the number of successes over the total number of people. And of course, Q is still the complement. So Q hat is 1 minus P hat. So don't get too caught up in all the terminology and the symbology. If I said there are 100 people in this hospital and 83 of them are blank, and I'm interested in blank, then my p hat is 83 out of 100, or 0.83. And q hat is simply the complement of that. It's just 0.17. So don't make this more complicated than it needs to be. Just try to understand the terminology and know that it is sometimes complicated to look at, but it's really simple ideas. Okay. In order to do a large sample confidence interval for P, n P hat and n Q hat both have to be greater than 15. If it's not, then you use something called Wilson's adjustment. And I'm not even sure, here it is right here, Wilson's adjustment. If unless n is extremely large, the large sample procedure performs poorly when P, the probability, the proportion is near 0 or 1. And if that's the case, then you use this adjusted Wilson's for estimating P. And then this is on page 278 if you want to review how to do this. It's simply that you take your P, instead of your P hat essentially, times 1 minus P hat, divide by n plus 4, and that becomes your new standard error. And then you're still multiplying by the critical z value here. Maybe it's 1.96, maybe it's not. And then that's what your margin of error is in your confidence interval. So it's the exact same type of idea, but instead of your square root looking like this, p hat q hat over n, your square root looks like this. It's p hat minus, and this is p tilde, 1 minus p tilde, which is essentially q tilde, over n plus 4. So the adjustment is you're not dividing by n anymore. You're dividing by n plus 4. But the rest of it is identical. It's the same exact setup, even though the symbols look different. Okay. And that was all of that. Sample size, this is pretty neat. Sample size, how do we know how to calculate a sample size? Right here on the bottom of page 283, there are these handy little formulas right here. And this one tells you that depending on what your sampling error that you desire, you can actually calculate what your sample size is going to be by running through this formula right here. And remember that you always have to round up, because if you're talking about needing 73.8 people, well then in order to satisfy that criterion, you need to talk to 74 people. You need to round up to the next person, even though you're arguably, getting more quote unquote people than you really needed. But you always round up, because if you don't and you only get 73 people, then you're not satisfying your need for 73.8 people. Okay, so that's that. Same kind of thing for determining sample size for P is on the next page, page 285. Now this I got a lot of questions about when we did this problem, this part of the class. So we've been talking about confidence intervals for X bar and for P, P hat, proportions, excuse me. You can also have confidence intervals for your variance, the sigma squared that we did back in the beginning when we set up all of the individual data points. We subtracted the mean from them, we squared the difference, we divided by the degrees of freedom, all that stuff. So depending on which data points are in your sample, when we go back to, where's my little drawing here, my little cloud drawing, depending on which people are in your sample, that's going to give you an S, right? So it goes to reason then that your S can have a range also. And if S can have a range, then your S squared can have a range. So we can have a confidence interval for variance. And this is how you would calculate it. The lower limit is, and the numerators are the same in both of these. The lower limit is n minus 1 times S squared. The upper limit is n minus 1 times S squared. The bottom are these chi-square values, and we just take this right out of the chi-square table, and you look for the correct degrees of freedom, which is n minus 1, of course, as always. The correct degrees of freedom, and then you're looking at alpha over 2, and then whatever the complement of that is, 1 minus alpha over 2. And so when you're setting this up in the one that this book uses, the chi-square table is, where is it? I can never remember how it's set up. The chi-square table in here is set up, here it is set up hang on. Here, chi-square. The critical values of the chi-square table are arranged in mirror order, essentially. So if you are in the second to left column for your this would be your upper limit. If you're in the second to left column here, then when you go for your other value, you're going to be in the second to right column, because they're mirror images of each other. So you'd be in the second to right column over here. But that makes sense, because if this is an alpha of 0.99, then of course you're going to be over here at an alpha of 0.01, right? So your second from right corresponds with second from left, and that's what would give you your two values, or whatever the case may be for your particular significance level. Other tables are different. I sent out one that has a large degree of freedom, and it was arranged exactly backwards. So just look at the headings of the table and see how it's set up when you're looking at one. Okay. We're going to take a break in about 10 minutes here for a couple minutes, and we'll come back and finish up the last couple of chapters of the book. Okay, so here on page 315 are some commonly used z-values. I just try to memorize these, and all of these can be pulled directly from the z table if you just, did a little bit of math, a little bit of just subtracting and figuring things out. So all of these are directly pulled from the z table, but they're just here, and I like to just commit them to memory, because you end up using a 0.05 significance level a lot. And so you end up with 1.645, 1.96, and even to a lesser extent, 2.33 or 2.575. And even that is a rounding, because I've used other books that call this 2.576 in the past. So it's just, that is what it is. Also, if you're not told anything in a problem, you always assume 95%, which means alpha is 0.05. You always assume that if you're not told otherwise. That's kind of like the general, the standard one. Okay. Okay. So calculating a p-value, this can seem really confusing because we rely on technology to give us our p-values so much, but think about it. P is either tolerable or it's not. If it's tolerable, it's within the bounds of your test. If it's not tolerable, it's not within the bounds of your test. A p-value is simply when you calculate your test statistic, your p-value is the tail that's left over outside of that test statistic. So just like when we chose our significance level, and that gave us an alpha value outside of it. So if we chose a 95% confidence level, the alpha value would be 0.05. Just like we chose that, we can then turn around and go to our data and calculate a test statistic, whether it's a t or a z or a whatever. We can calculate a test statistic, and that test statistic will divide up the distribution in a certain way. Let's say we calculate our test statistic and it goes to here, right? Whatever that number is, it's not the number we chose at the beginning. It's not 95. It's just whatever the data gave us. And then this tail is the p-value. That's the p-value. There's no formula for it. There's no, little cheat sheet, whatever. It's simply the area left over outside of your tail. And your tail is what's designated by your test statistic that you have calculated. So that's all the p-value is. And then we're just comparing if we choose 95% and that gives us a 0.05, and then we calculated this and it gave us a p-value, all we're doing here, the whole point in this whole class is learning how to compare these. It's learning how to compare this alpha value to this p-value. If p is lower than alpha, you reject the null hypothesis. If p is lower than alpha, then the alternative hypothesis is more likely, and vice versa. If alpha is larger, then the null hypothesis is more likely. So that's all that's about. I know p-values can seem kind of confusing, but they're really not any more complicated than that. And then we're going to make a big jump up here. We'll finish chapter 6, and then we'll take our break really quickly. So we talked about hypothesis tests, and everybody's comfortable with a null hypothesis and an alternative hypothesis. The null hypothesis, without even knowing anything about any problem, without even reading anything about a problem, you can assume that the null hypothesis is that nothing changed, that nothing happened, that nothing made it a difference, that nothing was different, that the population didn't change. Basically, the null hypothesis is nothing exciting happened. The alternative hypothesis is something exciting happened. Either something's larger or smaller, or something's different, not equal to, meaning different. That's the alternative. So if you're ever reading through a paper or something, or reading something, and it tells you it's describing the situation, but it doesn't actually state nulls or alternatives. If you're just reading through it and it gives you a p-value and says, oh, we ran this test and we got, or the data, you could even just say something as generic as data analysis yielded a p-value of 0.02. That's all you need to know. You could really forgo the rest of the paper, because if you know that the p-value is 0.02, then you know that they rejected their null hypothesis. You know that whatever they were doing, it made a difference. So you can decide right there if you're going to continue reading the paper or not. Okay. Okay, and that's the end of chapter 6. So we're going to take a break for about 5 minutes or so. When we come back, we'll do chapters 7, 8, and 9, and then and that's it. Believe it or not, we've gotten 2/3 of the book done, 2/3 of the whole class done. Anybody have any questions? Okay, so we will. Let me stop share. Then I'm going to pause the recording, and we'll come back in 5 minutes or so. And I see that Regina and Kenya joined us. Hello. Okay, see you guys back at 6:31. Okay, so we're back from our break. And we're going to do the last 3 chapters. So again, we're really getting into situations with the last 3 chapters where it's just a bunch of formulas, and you just pick whichever one you need based on whatever scenario you have. So you may be interested in a difference of means. Excuse me. You may be interested in a difference of proportions. By difference, I mean the mathematical difference, the subtraction of the two. You may be interested in comparing categories, in which case you'd be using chi-square. You may be interested in comparing more than one thing, more than one mean, in which case you would use ANOVA. You may be looking at something that's not normal, a distribution, a data set that's not normal, in which case you need to use a non-parametric test like a Wilcoxon test, or the sign test for medians, which is remember the eta, the Greek letter eta, that would be that one. So at any rate, there's just a lot of things in our tool belt, and we just have to be able to look around to the left or to the right side of the tool belt and find the screwdriver that we want and pluck it out and say, aha, this is what I need. Right here. Oops, I need to do this, don't I? Share screen to this. Why does Zoom do this? I do not know, but it like rearranges my entire computer when I do that. Okay, so I have my document camera up now. Hello. And so on page 371 is where I am right now. We've got these confidence intervals for a difference in means. This is a difference in means, mu1 minus mu2. And so if you look, these are exactly the same thing we've seen before. The structure is identical. So we have the X bar of the first population minus the X bar of the second population. And we're interested in the difference of those. So obviously that is our point estimate, right? That's obviously our point estimate. And then what do? Well, we plus or minus a margin of error. Margin of error, right? And that margin of error has the same structure every time. That margin of error has a structure of a critical z-value, whatever that z-value is. critical z-value, okay? In the book, it tells you alpha over 2, but it's some critical z-value. I'll just put a star by it. It's some critical z-value for whatever our alpha is. And then we multiply by some really nice big square root. And we're doing this. Normally, we would have like the s over the square root of n. This is a little bit different. It is the n1 and n2 on the bottom. If you know sigma, then you put the sigma squared in there and the sigma squared in there. If you don't know sigma, then you just replace this with the s. You just replace it. They're still being squared. You just replace it with s1 squared, and you replace it with s2. The s of the first population and the s of the second population. That's the only difference. That's a confidence interval for a difference of means. Difference of means. You also have test statistics. You can calculate a test statistic. For z, this is for a large sample for the difference of means. And it's the same kind of a setup. The difference is if you know sigma, use it. If you don't, just use s. But the rest of it is identical. The rest of it is identical. And I don't memorize these things, honestly. I look them up. I know, I mean, they all have about the same structure, so they're very predictable. But just to be really, certain that I haven't made a silly mistake, I look it up. I mean, there's no reason not to look it up, right? We can do the exact same thing I just talked to you about with a small sample with a t test. So we can do that. We have test statistics for t, and notice all of these are difference in means. These are all just about differences of means. So we can do all of that kind of stuff. One of the things we have to satisfy is equal variances, and if we don't have equal variances, then, or excuse me, no, yeah, I'm sorry, that's right. When we don't have equal variances right here, this is the sigma squared of the first population and the sigma squared of the second population. When we don't have equal variances, we have to adjust our confidence interval and test statistics a little bit. This is if we have equal sample sizes. This is where we have unequal sample sizes. But notice it's the same thing. This is all about comparing two means. This is all about a difference of means. It's the first population minus the second population, and it's the same for all of them. The format looks different because they've typed it out differently, but it's exactly the same thing as we've seen before. We have x1 minus x2 bar, we have our t, and then under the square root we have s squared over n and s squared over n. The test statistic follows the exact same thing. It's just it's the same format, but there's just slightly different ways of applying it. And if you're concerned, this is where we get into the non-parametrics. If you're concerned that the assumptions are not satisfied, like for example, it's not normal, you can use a Wilcoxon rank sum test. It's really easy to confuse Wilcoxon rank sum and Wilcoxon signed rank because they both have the word rank in it, but they're very, very different tests. We're going to get to that in just a second. Okay, paired differences. I would recommend everybody go to page 391. Whoops, page 391, and just review all of the paired difference stuff right here, because I know that can be really kind of tedious, and it's not complicated, but it is tedious. And so you have to be sure that you're not making any silly mistakes there. That's all that's about. Okay. Just review all the different conditions. Now this is a Wilcoxon signed rank test. This is what you would use if you are comparing two population means, and the normal distribution is not satisfied. Okay, and we'll go over that in a second. This is for paired differences. And so if they're paired, the main difference between a Wilcoxon rank sum and Wilcoxon sign rank, this is signed rank, is that the rank sum is for independent populations, okay? And the signed rank is for dependent populations. They're dependent, they're paired, they are related to each other in some way. That's a signed rank, Wilcoxon. If they are independent populations, it is rank sum, okay? And there should be very good example problems on a D2L going through all the details of those. They're very tedious as well. They're not hard, they're just tedious. And so going through Dr. Mistoli's example problems is going to be really good if you just work through it again from beginning to end and just work through it as she walks you through it. I mean, that's a really good way to do that. Oh, so if you're comparing two means, mu1 minus mu2, and you need to determine your sample size, this is the formula for that. You have the critical z-value, you have your variances added together, and you have your sampling error in the denominator. Okay. And a couple of variations for that as well, based on what kind of sample sizes you're looking for. So why Wilcoxon rank sum? Well, you would use a Wilcoxon rank sum when the sample sizes are equal. And the greater the difference in the rank sums, the greater will be the weight of evidence indicating a difference between the probability distributions. So you're looking at a difference in the probability distributions would mean that one bell curve is shifted to the left or to the right from the other one. And so the larger the differences are in between corresponding paired pieces, or excuse me, not paired pieces, the corresponding, the difference between the corresponding pieces from one to another, that's going to show you obviously a larger difference in the entire population, or excuse me, the entire distribution, not the entire distribution. And that's the idea behind the Wilcoxon test. And anyway, I would just recommend going through the examples that she's provided you again with that. I don't have any new ones worked up, but the best thing for that is just to go through them and go back and work through the same problems from the homework sets on those, and that'll be your best chance at reviewing those. I think that's the best way to do that. Okay. But if you're interested, the formula for the rank sum test is on page 407. It's right here. It's just more tedious than anything else. There's nothing real complicated about it. It's just very tedious. Paired difference experiment. This is if you have dependent populations. This is the Wilcoxon sign rank. Same kind of a thing, Wilcoxon sign rank for dependent populations where one piece of data is connected to another one. And then this is on page 416 and 417. Here's the formula for that. Again, it's not complicated. It's just a bunch of adding and multiplying and dividing and subtracting, but it's just very tedious to get there. Okay. When you're comparing 3 or more means, that is analysis of variance. That's ANOVA. If you're comparing 3 treatments for something, you know, that's what ANOVA is. ANOVA follows the F distribution, so you've learned about 5 distributions in this class. You've learned about the Z distribution, also called the normal distribution, normal curve. You learned about Z, you've learned about T, the T distribution. You've learned about the binomial distribution. You've learned about chi-square distribution. And you're learning about the F distribution. F is the ANOVA statistic. And so ANOVA, doing it manually is very complicated and very tedious. It's difficult just because there's so many parts to it. So for all intents and purposes, we just let computers do that. And we let computers tell us a p-value, and then we interpret the p-value from there. So for example, here is a ANOVA printout. Here's the F value. And here is the p-value. That p-value is so small, it's 0. That p-value is so small, it's definitely smaller than alpha, so we reject HO. The alternative hypothesis is more likely. That's what we would say there. I believe some of the questions on the final are going to use the terminology like SS, sum of squares, SST, sum of squares for treatments, SSE, sum of squares for errors, MST, MSC. If you just go back, that's the mean square for treatment and for errors. If you just go back and go through the questions from the homework assignment and the questions in class, you'll be fine with those kinds of things. There's not going to be a whole lot about that on there. And chapter 8, what did we do in chapter 8? All chapter 8 is just the exact same things that we did for difference of means, but we're just replicating it for difference of proportions. So we're taking a p-hat for the first population and a p-hat for the second population, and we're just looking at a difference in proportions, difference in percentages, basically. And so we have the same kind of stuff, and they even look identical. So we have the confidence interval for a difference of p-hats. We have the test statistic for difference in p-hats. And the same kind of thing for figuring out sample size needed. Same thing for a difference in p-hats. So all the exact same stuff from chapter 6. And then lastly, we get to the chi-square test. The chi-square test, which basically tests whether or not values you are getting, like your actual data values, whether or not they are the same as what you would have expected to get. So it compares directly, the chi-square test compares the actual values that you're getting with the expected values that you expected to get. That's what the chi-square test compares. And there are 2 types of chi-square test. There is a regular chi-square test. I don't know that it has another name, or maybe it's one way. It's a one-way chi-square test. And the one-way chi-square test, also called, like, I just call it a regular chi-square test. That tests, which is a little counterintuitive, a one-way or regular chi-square test will test whether or not values that are divided into a two-category system are what you would expect them to be. So generally speaking, if we're looking at the document camera here, generally speaking, if we have a table of values, and we have all these little values in here, whatever, and this over here is category 1, and this over here is category 2, and what the chi-square test tells you is, and of course these data can be categorized as category 2, and these are the ways they're divided into category 1. And so the chi-square, the regular chi-square test will tell you whether or not those two categories have a relationship to each other. It'll tell you whether or not category 1 influences or impacts, in other words, has a relationship with category 2. And you do that by finding the expected values for all of your cells here. And those are just simply the row total times the column total divided by the table total. And you just do all that for each of these things. And so this is what is your actual. And then you just run those little expected counts, and you get another table with, the same size table. And here's category 2, and here's category 1. And you've done all these calculations, and you find out this is what you were expected to get. Then the chi-square test will compare each value to its corresponding mate. So it would test this value to this value, and it would test this value to this value, and so on and so forth, to see overall, when we're looking at the entire thing, how expectable are our actual results. If they're really expectable, then the differences between these two are going to be small, right? And we're looking at the entire data set as one calculation. You don't run a chi-square test on one piece of data. You run a chi-square test on your entire data set, and you get one chi-square answer for the entire data set. Okay. There's another type of chi-square test called a goodness of fit, and it does the same thing, but for a little bit of a different scenario. And the reason it's a different scenario is, instead of having two different categories, the goodness of fit test, also called the chi-square GOF, G-O-F, goodness of fit, that tests whether or not only one category produces results that are expectable across all of the classes of that category. So a really good example would be like days of the week. Are all babies likely to be born on each day of the week? Or are babies more likely to be born on a Tuesday, or whatever the scenario is? So we might say, okay, okay, here's Monday, here's Tuesday, here's Wednesday, or Thursday, Friday, Saturday, Sunday. Okay, here's all the days of the week. And are all the babies likely to be born on each day? So the chi-square goodness of fit test is going to test whether or not there's an equal number of babies born each of these days, right? Because if there's no relationship, then babies are going to be, the same number of babies are going to be born each day, right? So we would test whether this is 1/7 of all the babies, and this is 1/7 of all the babies, and this is 1/7, this is 1/7, this is 1/7, this is 1/7, and this is 1/7. And we're going to test to see whether each day of the week is 1/7 of all babies. If that's true, then there's no relationship between days of the week and births. If it's not true, then there is a relationship between days of the week and births, because if it wasn't true, then we wouldn't be getting all of these 1/7, right? It would be different. So that's what the chi-square goodness of fit test does. And so if it says like, okay, so let's say we tested, we talked to 700 mothers. And so 700 babies, or excuse me, 700 births, not 700 mothers, 700 births. We looked at 700 births and what day of the week that they were on. So if there was no relationship between the day of the week and births, 100 is going to be on Monday, 100 is going to be on Tuesday, all the way out. All these are going to be hundreds. And then we actually look at the actual numbers. And let's say that there was 52 here and 117 there and 63 and 42 and 17 and whatever the numbers are. This is what we expect. We expect those, but we have gotten these. And then the chi-square test compares what we got to what we expected and looks at how much of a difference that is in there over the entire data set. Just like with the two category situation, it's looking at the categories' relationship to each other. The goodness of fit test is saying how well does the data fit this one category and what I expect the one category to give me. And the same thing comes out of it. There's a chi-square distribution that we just look up in the back of the book or look at a table. It gives us, this is the way that you calculate a chi-square statistic. You take the observed minus the expected over the expected and just square the numerator and then add all those things up. You get a chi-square statistic out of all that. You look it up in the back of the book, and that's also going to give you a p-value. That will also give you a p-value. If I can find it here. Here. Chi-square. So you look this up and you get your p-value, and whatever's in the table here is your p-value, right? And so that's what you would compare to your alpha, just like we've done before. You look up your critical value and then figure out how it compares to the other. This is how you calculate the expected values right here on the bottom of page 471. The expected value is the row total. This is the row total, this is the column total, and then this is the sample size, the total sample size, which is a table total. If you're calculating up people, N is the number of people you talk to. It's just all the people in the whole table added together. How many people are in there total? That's what that is. Okay. So another way you can think of the expected values is like, come here, is like row total times column total over table total. That's what an expected value is. And just if you you can take a minute and convince yourself that if you do this for any of these things, any of these row totals and column totals is going to have a unique combination for each element. And so you'll get a different number in each of these values. Okay. There's only one unique way to do that for each of those table elements. The last chapter, is this really taught the last chapter? Maybe, yeah, I guess it is. Linear regression. So there's two parts of linear regression. There's deterministic and probabilistic. The deterministic is simply just let's take this back to real basic terms here, and let's just go with y equals mx plus b, because we're doing linear regression here. So if it's y equals mx plus b, I want you to think of it like this. This is the deterministic part, and when we add this in, it's the probabilistic part. So that's the deterministic. It's just the direct relationship between x and y. Adding in this is the error. That's the probabilistic part. So, come here. Okay. So look at this. The deterministic component is merely the line intersecting at 0 here. The random error is the probabilistic part. And notice the difference here. The only difference between this one and this one is the random error. And all we're doing there is adding in this kind of residual, is what it's called, from the actual data point to the line itself. Okay. And of course we have excuse me. And so looking at the full probabilistic model here, this would be our y equals mx plus b, and the b right here, the y-intercept is just how much it's being shifted up or down, and the epsilon is the random error that accounts for the residuals. So if you want to think about it as y equals mx plus b, it's really y equals mx plus b plus error. Okay, y equals mx plus b. This will give you the deterministic part. This is just the regular line that gives you, you know, an old line like that, or maybe a line up here. And then the error is what is actually this part right there. It's how far the point is off of the line compared to where it should have been. Okay. And least squares, that's a good way to do that. It's just very tedious. I would recommend doing all of your least squares work in Excel, just because it makes it a lot easier there. Just do little columns like that. Oh, r squared, the correlation coefficient, r squared. So we've all seen in Excel, we've all done, you know, lines of best fit, or Excel calls it a trend line. And the trend line gives us an r squared value. And what the r squared value is telling us is what percentage of the data falls onto the line. So this is a trend line, and you know, we have stuff all over the place here, whatever. And we're really wondering about how well, how efficient, how perfect is that trend line at representing the entire data set. And so your values for R go from 0 up to 1, and they can be positive or negative. If it's positive, it just means that it's a positive slope line like that. If it's negative, it's just a negative slope line. And if you have trouble remembering, you know, which one is which, if Slope Dude, if you've ever seen the video for Slope Dude, I love Slope Dude. Slope Dude is a skier, and he skis from the left, and he's puff, puff, positive all the way up the mountain, and then he's skiing down the mountain, nice, negative. This is nice skiing down the mountain, okay? But he always skis towards the right. Otherwise, we're totally backwards. So this is puff, puff, positive all the way up the mountain. This is nice, negative. R squared can be positive or negative. If it's positive, it just means that not R squared. R can be positive or negative. if you take the square root of r squared kind of tells you the percentage of it in there. And if you take the square root and it's, you know it's positive if the line is going up and it's negative if the line's going down like that. So that's the r squared. And that's it. Non-parametric test for correlation. I don't think we actually did. Oh, Spearman's. Yes, Spearman's. Yes, of course. Spearman's coefficient. So with the Spearman's test, did we do Spearman's in this class? Somebody tell me. I can't remember.
Yes.
Yes, okay. That's what I thought. So for Spearman's, this is what you need to know. Right here, bottom of page 556, you need to know this is the shortcut for Spearman's rank correlation here, okay? And so the DIs are the differences in the ranks of the ith observations for sample 1 and sample 2. So if you, excuse me, if U is the ith observation in sample 1 and V is the ith observation in sample 2, then the DIs are those differences of those ith samples. And then you square those differences. You square the differences. Add them up, multiply by 6, divide by n times n squared minus 1. It's a little bit different there. Honestly, I don't know why Spearman's is set up like this, but whoever Mrs. or Mr. Spearman is or was could probably answer that question for you. I certainly can't. So you do all that, you subtract it from 1, and that gives you the R for the RS is like the R sub Spearman, the Spearman R, okay? So I think that's it. That's it. That's everything. That is everything. What questions are there? By the way, has everybody looked at the practice final exam? I hope. You need to do that practice final exam. Just sit down and go through the whole thing. Because the real thing will be very much similar to that. Good. Thank you, Janet. Great. Well, I'm going to go ahead and stop the recording.